We've all heard the promise of fusion energy, right? Clean, almost limitless power, just like the sun. But for decades, there's been this one stubborn mystery holding us back. It's like we're trying to bottle up a star, but something is stealing all the heat. So today, we're going to do something a little different. We're not treating this as a physics problem. We're treating it like a crime scene. A massive energy heist is happening, and we're going to find the culprit.
Okay, so let's get right into it. The central question for our investigation is pretty simple, actually. We are pumping incredible amounts of energy into these fusion reactors, but it's just vanishing before it can do what it's supposed to do. So what's the deal? Where's all that energy actually going?
You know, the basic challenge with fusion is all about containment. You have to heat a gas to over 100 million degrees, hotter than the core of the sun, until it becomes a plasma. And at that temperature, no physical material on Earth can touch it. So the solution is this amazing magnetic bottle. Basically, a super powerful magnetic field shaped like a donut that holds the plasma in place. The problem? This bottle is super leaky. It's like trying to carry water in a bucket that's just full of holes. The heat is just pouring right out.
Now, every good detective needs that one critical piece of evidence, right? The smoking gun. Well, this is ours. 0.90 seconds. This is the real measured energy confinement time from a huge experiment at the jet reactor. It tells us exactly how long a bit of heat hangs out inside the plasma before it escapes. Any theory, any suspect we bring in for questioning has to explain this number. Remember it.
All right, let's meet our first suspect. This is the obvious one, the one you'd check out first at any crime scene. We're talking about simple, everyday particle collisions. In the world of plasma physics, this is called classical transport. So the method here is really straightforward. Just imagine the plasma is a giant, chaotic game of cosmic billiards. All the particles are just constantly bumping into each other, and with every little bump, they get knocked a tiny bit off course until they eventually just stagger their way out of the magnetic bottle. Honestly, if this were the whole story, we'd probably have fusion power plants all over the grid today.
So, let's check the alibi. Does this simple story actually hold up? We can calculate exactly what the confinement time should be if it was just these simple collisions. How does that prediction compare to our hard evidence?
And boom, right away this suspect's story completely falls apart. The theory predicts the heat should stick around for 670 seconds, but the experiment says it's gone in less than 1 second. That's a mismatch of more than 700 times. It's not even in the same universe. So yeah, suspect number 1 is definitely cleared. This heist is way more sophisticated than a simple smash and grab.
Okay, this brings us to suspect number 2. This one's a bit more of a complex character. It understands the layout of the reactor, so to speak. We're going to call it the donut effect, or, if you want to be formal, neoclassical transport.
See, this is where that donut shape changes everything. Because the magnetic field is stronger on the inside of the donut and weaker on the outside, the particles don't just spiral around nicely. Nope, they get caught and forced into these big sweeping paths that look like, well, bananas. And these banana orbits are a much, much faster getaway route than just slowly bumping your way out. This theory definitely sounds a lot smarter, right? It's taking the complex geometry into account. So the big question is, does this suspect explain our magic number? Does it explain the 0.90 seconds we saw for real?
Well, we're getting warmer. The prediction this time is 11 seconds. Now that's way better than 670 seconds for sure, but it's still more than 10 times longer than the 0.90 seconds we actually saw in reality. So what does that tell us? It tells us these banana orbits are part of the gang, but they are not the ringleader. There's a much bigger operation going on that we still haven't accounted for. So after we've eliminated the simple-minded crook and the slightly smarter accomplice, we're left with the true mastermind of this whole energy heist. It's not a single particle, it's not a predictable orbit. The culprit is a collective, chaotic, and incredibly powerful force: turbulence. I want you to forget about single particles bumping around. Picture a hurricane. Inside the plasma, turbulence creates this storm of countless tiny swirling vortices or eddies. And these eddies all link up, creating these chaotic, fast-moving channels that act like a superhighway, just flushing the heat from the blazing hot core out to the cooler edge. It is an organized chaos that is ruthlessly efficient at stealing energy. Okay, let's put all the evidence up on the board. This is the moment of truth. We've got our key experimental result, that 0.90 seconds, and right next to it, we're going to line up the predictions from every single one of our suspects. And there it is, clear as day. Classical theory, 670 seconds, way off. Neoclassical, the donut effect, 11 seconds. Getting warmer, but no cigar. And then,
turbulence. Its prediction, about 0.4 seconds. It's the only one that's even in the same ballpark. It's the only one that can explain the scale of the crime. We found our culprit. Case closed.
So finding the bad guy is one thing, but bringing them under control? That's a whole different challenge. Now that we know turbulence is public enemy number one, how in the world do scientists actually fight back and try to tame this wild plasma storm?
And, it gets even trickier, because turbulence isn't just one single thing. It's more like an organized crime syndicate with different gangs, and each gang has its own specialty. You've got the gangs that are experts at stealing heat from the ions, others that go after the electrons. To tame the storm, you have to understand and control all these different players.
The strategy isn't to just wipe out turbulence completely. That's probably impossible. Instead, it's way more clever. Scientists found they can actually change how the reactor operates to force the plasma into different states, or regimes, where the turbulence is just way less severe. It's kind of like changing the environment to disrupt the gang's operations.
The two most famous of these regimes are L mode for low confinement and H mode for high confinement. H mode is amazing. It creates this kind of sharp wall at the edge of the plasma that smothers turbulence and basically doubles your confinement. The problem? The pressure builds and builds until it erupts in these violent bursts, like tiny solar flares that could damage the power plant. Then there's L mode. It's much steadier, much safer, but the performance just isn't as good. It's that classic trade-off, high reward, high risk, versus safe and steady.
So why does this scientific detective story matter so much? Because solving this energy heist, learning to control this turbulence, isn't just an academic puzzle. It is the single most important key to unlocking practical, affordable fusion energy for all of us.
So what does better confinement actually look like in the real world? Well, it looks like this. $4 billion. That's the potential cost savings on a single fusion power plant if we can just get better at controlling this turbulence. And this quote really says it all. The road to cheaper fusion power isn't just about building bigger magnets. It's about better physics. Understanding and taming that turbulent storm inside the reactor is the biggest lever we have to make fusion energy a reality. So, we've identified the main culprit in fusion's great energy heist. We know it's turbulence, and we're developing these incredibly clever strategies to keep it in check. Our investigation has led us to a crucial breakthrough, bringing us closer than ever before. But it also leaves us with the ultimate question. Now that we know who the enemy is that enough to finally win this war and build a star on Earth?